Hi guys, so this is Galactic Dynamics lecture 7. Okay, so we had been studying trajectories that stars follow in a given type of potential, right? So if you have some sort of matter distribution which gives rise to some kind of gravitational potential, so how a test particle behaves, or in our case, how a star, the projectile of a star would be in such a system, right? So in the last lecture, we studied spherical potential. We did this exercise of trying to know how the orbit looks like and how different properties of orbits behave in spherical potential, and we saw that the total angular momentum is conserved, and the z component of total angular momentum is conserved, of course, and the energy is conserved as well. So in most of the cases, as long as Hamiltonian of the system, which is basically canonical kinetic energy plus canonical potential energy, the definition of Hamiltonian, as long as Hamiltonian is explicitly time independent, the energy comes out to be constant, so the energy is conserved. So the total angular momentum and the energy for the spherical potential case were conserved, are conserved, right? And these and the energy and the total angular momentum is thus called the integrals of motion, because they remain constant as the orbit evolves, or through the path of the star, these two quantities remain constant. As an application, we solved the trajectory for the Kepler potential, right? Uh, in this lecture, we would be doing something similar, but for the axis symmetric case instead. So previously, we studied matter distribution. We studied axis symmetric system, right? Given the matter distribution and using the Poisson equation, we tried to find out the gravitational potential and vice versa, and we saw how the profile of such systems looks like in matter density space and in gravitational potential space, right? So our galaxy, it can be very well approximated, in fact, as axis symmetric system, right? So the stellar population, so we are not considering the dark matter distribution right now. We are just considering how the stars, what profile does the star follow in our galaxy. So our galaxy can be very well approximated as axis symmetric system. And uh, if we approximate it further, we can boil down our system to a disk galaxy, right? Or we can say that our galaxy looks like an exponentially decaying disk, where this part happens to be the bulge, right? Very much concentrated in the number density of stars, and then the density sort of decays along the z-axis. So this is how the density looks like, stellar matter density looks like in our galaxy, right? So r naught and z naught sets the scale of this profile decay. Okay. Which is, of course, so r naught and z naught are the parameters which could be different for different galaxies which have axis symmetric profile. Okay, so let's see how the motion of the stars, or what the orbits comes out, how the stars behave in such a system. So let the potential be phi rz. Let the potential be phi depending on radius and z-axis. So we'll be dealing in cylindrical coordinates now, because the best coordinate system to deal with axis symmetric system is the cylindrical coordinate system. So the system, it's symmetric about z-axis, and since it's an axis symmetric system, this means that there is no azimuthal angle dependence, right? So it just depends on radius and z and not on the angle phi. Okay, so please don't confuse yourself, because I'm using phi as the gravitational potential as well, and phi as the azimuthal angle as well, which goes from 0 to 2 pi. So I'm sorry about that nomenclature, but that's the best and the most common jargon that we use in physics for azimuthal angle and gravitational potential. So the motion of a star, generally the motion of the star could be given by this equation right here, where d square r, where r it's the position vector, over dt square it's basically the acceleration, equals minus del of phi, which is basically the force. So we are considering this equation for a unit mass. So if we try to, if you're really interested in finding the motion, the equation of motion for the star, so we would write the Lagrangian of the system as kinetic energy minus potential energy. In cylindrical coordinate, this term over here, it's the kinetic energy, where r dot square is the kinetic energy in radial direction, plus r square phi dot square, which is kinetic energy in the azimuthal direction, plus z dot square, which is the kinetic energy term in the z direction, minus the potential energy, right? So the Euler-Lagrangian equation of motion is given by this equation over here, where q it's the canonical coordinate, in our case r, phi and z, and q dot are the canonical velocities, which is r dot, phi dot and z dot in our case. So if you try to find out the Euler-Lagrangian equation of motion for r in r coordinate, in phi coordinate and in z coordinate, this is what we get, right? So this over here, it's the equation 1, r double dot minus r phi dot square equals minus del phi by del r. For phi, we get d dt of r square phi dot equal to 0. So del L over del phi does not exist, because there is no phi dependence in the kinetic energy and there is no phi dependence in the potential energy as well, since it's axisymmetric system. So d dt over r square phi dot comes out to be 0, and we call this quantity r square phi dot as z component of angular momentum. So if there is an orbit in phi in z equals 0 plane, for example, and it's orbiting in a circular or elliptical direction, its z component of angular momentum, it remains constant. So we have found one integral of motion, the integral of motion being the quantity that remains constant as the orbit evolves in time, right? And for the z direction, the Euler-Lagrangian equation of motion is simply z double dot, the acceleration in z direction, equals minus del phi by del z. Okay. Now generally, the equation 1, 2 and 3 for quite simple and analytically solvable potential, one can solve 1, 2 and 3 equation analytically, and then can find r in terms of time, and phi dot or phi in terms of time, and z in terms of time, that how the orbit evolves in radius, azimuthal angle, and z coordinate, right? But usually it's not so simple. So the evolution of orbits can thus be studied by numerical integration, right? So you take the help of computer and you try to integrate these equations to know how r, phi and z evolve in time. Now let's consider equation 1 that we had. So r double dot equals minus del phi by del r, del phi over del r plus r phi dot square. Using equation 2, which basically defines the z component of angular momentum over here as r square phi dot. So using equation 2 in equation 1, here we get minus del phi over del r plus r times Lz square over r to the power 4. And I missed a step, but it's a straightforward one, that if you these two terms right here can be written as minus del over del r of this total term, right? And we call this phi plus Lz square upon 2r square as phi effective. So this is the effective potential that a star sees in an axis-symmetric system, right? So so just by definition, we are just saying that phi plus Lz square upon 2r square, just we are giving it a name as phi f, which is phi effective. Our aim here, our equation, the 3 equation of motion basically boils down to 2 equation of motion, in fact, where The first one being the R double dot equals minus del phi effective over del R, where phi F, it's the effective potential. And the second equation being Z double dot acceleration in Z direction equals minus del of del Z of phi effective, right? Because we know that del of del Z of this term, LZ square over 2R square, it's 0, right? So from equation 3, we had Z double dot equals minus del phi over del Z. But we can include this term within that phi. If we include plus LZ square over 2R square with phi, it won't make any difference to Z double dot, because when del over del Z would act on LZ square plus 2R square, it would still be 0, right? So we get these two as the equation of motion. So idea here is to is that the 3D problem, so basically what we've done here is that we have reduced 3D problem of R, phi and Z to a 2D problem, making use of the symmetry that the system, it's axis symmetric, right? So in all our studies, the first aim of any study is to see the symmetry of the system, right? The different symmetry of the system. Just by looking at the potential that it is phi independent, this means that the three equation of motion in R direction, in Z direction and in phi direction basically should boil down to only two equation of motion, since the system is independent of one of the coordinates, which happens to be phi right now, right? So just beforehand, just by looking at the system, we already knew that there should be at maximum just two equation of motion that should describe the entire system, and we have these two equation of motion right now, making use of the fact that the system, it's independent of azimuthal angle. We basically include this idea that system, it's azimuthal angle independent by introducing by incorporating LZ into the phi into the gravitational potential of the system, right? So suppose so here I'm giving a graph for a phi effective given by this function half of v naught square natural log of r square plus z square over q square plus lz square over 2r square, right? So basically this first term over here is the potential energy of the system. So for v naught equals 1, q equals 0.9 and lz equals 0.2, you would get a graph for equipotential surfaces, something like this, right? So you can try this with your computers or online graph plotters, that if you try to plot this function over here for these parameters value, you would get an equipotential surface of this kind. So we define ellipticity for this this potential as 1 minus q square equals 0.1. So basically, if q had been just 1, these equipotential surfaces would have been spherical, right? Because then if we just hide q here, if q is 1, basically q, it's hidden. So it's just half u naught square log of r square plus z square. So this happens to be a spherical system. But if q takes some value, then there happens to be certain kind of ellipticity that exists in the gravitational potential, and that's given by 1 minus q square. Okay, this is just for you to visualize how the system looks in potential space. Okay, so now let's try and find out the minima of phi effective. So the idea of finding minima is to find the most stable configuration, right? So to find out that at what value of radius or at what value of z, the system has the most stable configuration, or where the system has the least entropy, the least disorder in the system, right? And for orbits, this happens when orbits are circular. So what we are trying to do here is to find out that what's the condition for orbits to be circular in such a system, right? So the minima of phi effective, so the way to find minima is to extremize the function for which you're trying to find minima. Here the function happens to be phi effective. So we substitute del phi effective by del r equals 0 and del phi effective over del z equals 0, and the value of R and Z that one would get after making the substitution, given the form of phi effective, that set of value of R and Z would give you the condition for minimum phi effective and thus the condition for circular orbits, right? Now it's obvious that for equation 5 is satisfied everywhere on the equatorial plane, meaning the equatorial plane means the z equals 0 plane, right, where the equator lies. So just a jargon, and say that del phi effective over del r is 0 at r equals rg. Just say, because we are just generally studying right now, we do not have a form of phi effective. So say that at radius equals rg and at z equals 0, the equatorial plane there so this is the condition for minimum phi effective, say. So at this condition, del phi effective over del r is 0. So now we are substituting phi effective as phi plus Lg square over 2r square, right? And evaluating those value at Rg, at R equal to Rg and Z equal to 0. So this bar with the subscript of this set means basically we are evaluating this derivative at R equals Rg and Z equals 0. And the second term Lg square over 2r square, we are evaluating this derivative at R equals Rg and Z equals 0, right? So these two terms sums up to be 0, and taking this, the second term on the right hand side, this is what we get. So del phi over del r when evaluated at Rg comma 0 equals Lg square over Rg cube, and substituting for Lz we get Rg phi dot square, right? So this is the condition for circular orbit with angular speed phi dot, right? So what this tells us is that minima for phi effective occurs at radius at which circular orbit has angular momentum Lz, right? Or where the circular orbit has angular momentum Lz, or where the circular orbit has angular speed phi dot. That's where the phi effective, the minimum for phi effective occurs, and the value of phi effective is then given by phi at Rg comma 0 plus Lg square over 2 Rg square, right? So in general, you could note this, that in general the total energy in an arbitrary axis symmetric potential system, the total energy, or the Hamilton, is given by kinetic energy plus potential energy, which is energy equals half of the kinetic energy in cylindrical coordinates plus the potential energy. And since we know, we have defined our phi effective as phi plus Lg square over 2r square, so we can substitute Lz in place of phi dot here, right? And we would get our energy in terms of half of r dot square plus z dot square plus phi effective. So phi effective depends only on r and z, and of course Lz, but Lz is the constant of motion. So phi effective depends only on r and so phi effective only depends on r and z, and the kinetic energy also depends only on r and z. So basically our energy depends only on it's a four-dimension it's a four-dimension space that we are dealing with, given the initial condition in terms of energy and Lz, which remains constant throughout the evolution of orbit. We just need to take care of four other quantities, which is r and z, and r dot and z dot, right? Okay, so we know that the condition for circular orbits occurs at radius equal to rg and z equal to 0, so in equatorial plane. So now we are bound in the equatorial plane, because we know that's where the minima for phi effective occurs, and let's explore it more. Okay, so as can be seen from here, that Rg and Lz and phi dot, they are related, right? So Lz basically, so LZ depends on the initial condition that is provided to the stars, and once that initial condition is set, the LZ is set and the RG is set as well. So RG and LZ, they're part of the initial condition that do not change. So if a star is given a perfect initial condition so that it remains in the radius RG, and it will have a constant LZ as well, right? So let's now study about nearly circular orbits, the epicycles and velocity ellipsoid. So we know that generally in a system, nothing's perfect. Everything is it's in a sort of random motion, and we know by the study by observing nearby and far off stars, we know that stars are in our galaxy, or for matter of fact, for in any galaxy, stars are not on perfect circular paths, right? Stars form epicycles. So basically, if this is the circular path that star would have followed, provided that they were set off from the perfect initial condition for circular orbit. They're not exactly on the circular orbit, rather they kind of oscillate about this orbit, right? So they kind of oscillate. So they form a rosette, but not a very, very wide open rosette, but they sort of oscillate just around this circular orbit. Okay. So we know that RG happens to be the condition for a circular orbit. Let's say what happens when the initial condition is R, which is RG plus X. So let's see that if we provide a little perturbation in RG, so RG goes to RG plus X instead, what happens? This means that X equals R minus RG. And we know that X comma Z equals 0 comma 0. It's the minima for phi effective, because at X equal to 0, R equals RG, right? And we know that the minimum of phi effective occurs at RG and Z equals 0, right? So now let's expand phi effective around this this condition. So by Taylor expansion of phi effective about X comma Z equals 0 comma 0, this is the expansion right here, which is phi effective evaluated at X equals 0, Z equals 0, plus del phi effective over del R evaluated at 0 comma 0 times X, plus del phi effective over del Z evaluated at 0 comma 0 times Z, plus, so this this evaluation takes place only, I hope you guys are you know about Taylor expansion, right? So this 0 comma 0 applies only to this term, and the 0 does not apply to Z. This derivative, it's being evaluated at 0 comma 0, and this is multiplied by Z then. So phi effective, it's basically a function of R and Z, or X and Z in our case, plus half of, so this was the constant term, this is the linear term, and now let's move on to the quadratic term, the higher order term, which is half plus del square phi effective over del R square evaluated at 0 comma 0, since we are expanding phi effective about 0 comma 0 times X square, plus similar thing for Z square, and plus the higher order terms that exist. So this is the epicycle approximation, that we're not considering the higher order terms because we know that would be very small. Since if our X, it's very tiny, this means that X cube or X to the power 4 would be very tiny, and that can be neglected, right? Now this term, when evaluated at 0 comma 0, would be a constant, right? Because we would substitute R as RG, and we would substitute Z as 0, and that would give us the minimum value for phi effective, which is constant. Plus this term would be 0 over here, because we know when del phi effective over del R at X equals 0, meaning del phi effective over del R at R equals RG, we know that's the minimum condition for phi effective, so this term would boil down to 0. And similarly, del phi effective over del Z when evaluated at Z equals 0 would be 0. But these terms would not be 0, and they would and we'll just write them as half of del square phi effective over del r square at rg comma 0 times x square. So x equals 0 means r equals rg plus half of del square phi effective over del z square evaluated at rg comma 0 times z square, right? So basically phi effective boils down to a constant term plus this term over here, I'm calling it kappa square. So it's not k. Forgive my bad handwriting. It's kappa, right? So half of kappa square times x square plus half of nu square times z square. So where kappa square, it's del square phi effective over del r square evaluated at rg comma 0, and nu square equals del square phi effective over del z square evaluated at rg comma 0. So if it has not already hit you, this potential looks like a two-dimensional harmonic oscillator potential, because we know a one-dimensional harmonic potential looks like phi going as half of k x square, right, where k happen to be the string constant and x happen to be the displacement from the equilibrium position. So this is a two-dimensional harmonic oscillator potential in xz plane. So basically in radius z plane, x, it's like radius. So the equation of motion can simply be given by, for this gravitational potential over here, as x double dot, where double dot of course means the the second order time derivative of x equals minus kappa square x, and z double dot equals minus nu square z. So this equation, it's in the z direction, and this equation, it's in the radial direction. Now kappa and nu are epicycle and vertical frequencies, right? So we know from the equation of motion of a simple of an harmonic oscillator that x dot equals minus omega square x, basically, where omega happens to be the frequency or the angular frequency of the system. So this equation is basically tell us that there is some sort of oscillation about the radius direction, and this equation tells us that there is certain kind of oscillation in the z direction, right? As I was just mentioning earlier in this diagram, that stars generally do not follow exactly the circular path, because had they followed exactly the circular path, this means there is no oscillation in the r or in the z direction, right? There's just oscillation in phi direction, but do not confuse yourself. I mean, circular orbit has oscillation, of course, but in the angular, in the azimuthal angle direction, but not in the r or in the z direction, right? But here, using the epicycle approximation and evaluating phi effective in the vicinity of the circular orbit condition, we find out the equation of motion that happens to be similar to a two-dimensional harmonic oscillator in radial and z direction. So kappa and nu are the epicycle and vertical frequency. So given the top view of the trajectory of stars, if this is the circular orbit that the star might have taken if the initial conditions were perfectly aligned with the circular orbit initial condition, but if it slightly happens to be away from the initial condition for the circular orbit, the orbit oscillates in the radial direction. So if the galaxy is viewed from the top, from North Galactic pole, for example, and the sun, it's about 8 kiloparsecs away from the center. So suppose this is the galaxy and this is the center of the galaxy, and here it's the sun. So sun, it's not on a circular orbit, it's approximately on a circular orbit, or in fact it has certain oscillation in the radial direction, which is given, and the frequency in radial direction is given by kappa. And at the same time, in the z direction, so at the edge-on view, if you see galaxy from the edge, at the same time, so at the time when there is radial displacement, when there is radial oscillation, right, there is also z oscillations, right, up and down, like this. And the frequency for this up and down in z direction, this oscillation is given by nu over here. So let's rewrite 1 and 2. So kappa square, which is the frequency of star in epicycle approximation in radial direction, which is del square phi effective over del r square evaluated at rg comma 0, and we are just substituting for phi effective, which is phi plus lz square over 2r square, and we have evaluated the other term, the other term already. Let's call it equation 3. And nu square, which is del square phi over del z square evaluated at rg comma 0. Now we know that the circular velocity is given by r d phi by dr. I hope you remember this from our previous lectures. And we know that the circular velocity, it's given by omega square r square, where omega happens to be the angular frequency, right? So right here, this is the capital omega square r square. So the circular velocity is related to angular frequency and at a radius r by this equation here. This implies that the circular frequency, the angular frequency omega square, equals taking this on the left hand side downstairs, the r and r would cancel. So the circular frequency, making use of this equation, the circular frequency is given by 1 over r times del phi over del r evaluated at rg comma 0, which is lz square over r to the power 4, right? Because we know because we know that lz equals r square phi dot. So we know that what the omega square would be, right? Using the definition of lz, we know the value of omega square. So we know from this equation that this is omega square, and using the definition of lz, which is r square phi dot, we know that omega square also equals this. So now let's simplify. So basically what we are doing here, we are trying to find out kappa square and nu square in terms of observables, right? Because we want to know the values of kappa square and nu square using the parameters that one can observe from telescope, for example. So we just want to write kappa square and nu square in terms of observables. So kappa square equals del square phi over del r square plus 3lz square over rg4, right? So yes, so kappa square equals del of del r of lz square over r cube, right? Plus 3 times omega square, making use of equation 3 and this equation over here. So basically kappa square, so this omega square comes because we know that in equation 3 lz square on r to the power 4, so I just substituted for omega square, and del phi by del r is given by, from here I substitute for del phi by del r. So here this is del square over del r square, so del r, so this equation, so this term basically is del r of del phi by del r, and del phi by del r I substitute from here, so this goes here, and for the second term I just substitute omega square directly from here, evaluated at rg comma 0. So all this is being done at rg comma 0, which is the minimum condition for phi effective and which is near about the circular orbit condition, right? So this term boils down to ddr of r omega square, right? Because lz square over r cube, if r goes here, so this is r omega square plus 3 omega square. And if you apply the chain rule, so kappa square boils down to r times dr of omega square, the circular angular frequency, plus 4 omega square, everything evaluated at rg. So what happens is, now suppose you're observing a star, so you know your cylindrical coordinate radius to that star. When you're making an observation, you can observe the circular frequency of that star. Because you can study the proper motion, and you can observe proper motion, you can observe radial motion. So you know the circular frequency of the star. I mean, we have the technology to know the velocity of stars. So you know R, you know how omega evolves with R, and you know omega because you can observe it. So you observe omega square and you evaluate kappa square. So this is a good thing because since if you know kappa square, you basically locally know what phi effective or phi looks like, because if you know omega square, you know velocity, you know distance, you can evaluate Lz. So the thing that remains is what gravitational potential looks like. It looks like locally, because this is everything that's happening locally, right? Because the dynamical time, it's so huge. So if you observe, if you're somewhere here and you observe something at a distance, you know how locally gravitational potential behaves, and that's the entire idea of studying astrophysics, to know gravitational potential, because everything is ruled by gravitational potential. And again, using the Poisson equation, you can know the matter density existing in that region, right? So just to give you some numbers so that this theory becomes little realistic and easy to absorb, the circular frequency of galaxy does not increase as a function of radius, and we know this using the velocity curve. The velocity curve, it's the horizontal curve as we have seen before. So at r, at radius equals 8 kiloparsec, which is basically the distance between the center of the galaxy and the sun, the kappa, the radial frequency, is 36 kilometer per second per kiloparsec. And this is the uncertainty in the measurement, because when you have telescopes, you make observation, there is always some kind of uncertainty. So you never end up with an exact value, and this plus minus 10 comes because of the uncertainty. And kappa naught over omega naught, so this ratio comes out to be 1.3, again plus minus 0.2, which is some uncertainty. So kappa naught, it's the epicycle frequency, which is the frequency in the radial direction, and omega naught, it's a circular frequency, which is just circular frequency. So kappa naught over omega naught equals 1.3. This, what it means is that sun makes 1.3 oscillation in radial direction in time, in the same time that it takes sun to complete one circular orbit, right? So when omega naught, so in the time that omega naught is 1, that it starts from say phi equals 0 and it comes back to phi equals 2 pi, that's 1 omega naught. In the same time, k naught, it's 1.3. So there is so if you can see this figure clearly, the dashed lines is the circular orbit, and the black curve, the continuous curve, it's the radial oscillation that I'm trying to draw here. So in the time that omega naught is 1, that from the azimuthal angle phi equals 0, the sun goes and then comes back to phi equal 2 pi. So this is omega naught equals 1. In the same time, in the radial direction, the sun makes 1.3 oscillation. So if you imagine a wave with crest and trough, for example, so in the radial oscillation, so this is crest. In the radial direction, this is the starting position. So in the radial direction, this is crest, this is trough. I'm sorry. So this is crest, this is trough, and this is 1 here, because crest and trough, so it's back on the mean position, right? So this is the mean position, and then it grows in amplitude in the crest, and then it grows in the negative side of the amplitude in the trough, and then it comes back to the mean position. So this is kappa naught equals 1. And then there is again crest, so this is 0.3 of kappa. So in the radial direction it's 1.3, and in the azimuthal angle it's 1, right? So this is what we learn about our sun, that our sun, it's not exactly following a circular orbit. Just to end up things, we get two integral of motion, one in the radial direction given by half of x dot square plus kappa square x square, where x dot it's the kinetic energy in the radial direction and this is the potential energy in the radial direction. So this is energy in radial direction and the energy in z direction is given by half of z dot square plus nu square z square. Now this looks like motion of two independent decoupled oscillators in r and z direction, right? And generally, given the initial condition, one can write how how the z component of orbit evolves in time, and how the x, the radial component of orbit, evolves in time, where z and x are the amplitudes in z and r direction, nu and kappa are the frequencies, t is the time, and j and psi are the phase, which depends on initial conditions. So this is it for today's lecture. Thank you so much for listening. Ciao.